In 2020, OpenAI researchers looked at the chaos of deep learning training and found something impossible: precision. In a field dominated by trial and error, lucky hyperparameter tuning, and architectural guesswork, they discovered physics. They found that if you ignore the microscopic details and zoom out, the performance of a language model ceases to be random. It follows precise, smooth laws spanning more than 7 orders of magnitude. To see these laws, we must ignore layers and activation functions and focus strictly on 3 variables. First, n, the number of parameters. The paper explicitly isolates non-embedding parameters. We strip away the vocabulary lookup table. We only count the dense weights doing the reasoning. Second, d, the dataset size, measured in tokens. And third, c, the compute budget. We measure this in petaflop days, the number of days a system doing 1 quadrillion operations per second would take to finish. N, d, and c. These are the levers of scale. Deep learning intuition says architecture is everything. The data says it's irrelevant. Within reasonable limits, if you hold the total parameter count n fixed, the shape of the model doesn't matter. Take a deep, narrow model and a shallow, wide model. If they have the same parameter count, they land on the exact same point on the loss curve. The raw capacity to store information outweighs how you structure that storage. So, if architecture is noise, size is signal. The paper establishes a strict power law. Loss, as a function of parameters n, equals a constant divided by n raised to the power of 0.076. Look at that exponent. It is tiny. This implies massive diminishing returns. To have your error, you can't just double your parameters. You have to scale them exponentially. This straight line holds steady from a tiny toy model with 768 parameters all the way up to a 1.5 billion parameter giant. Data obeys the same physics. Using the WebText2 dataset, roughly 23 billion tokens, the authors found a similar power law. The loss scales with dataset size d to the power of negative 0.095. This is slightly steeper than the parameter scaling, meaning performance is technically more sensitive to adding data than adding neurons. But the mechanism is identical: predictable logarithmic tracks that let you calculate loss before training even begins. But you can't scale one variable in a vacuum. If you pump up model size n without feeding it more data, you hit a wall: overfitting. The paper derives the exact point of failure. The penalty depends on the ratio of n to the 0.74 power divided by d. That exponent is the recipe. It tells us that if you scale your model size by 8 times, you don't need 8 times more data. You only need about 5 times. Large models are surprisingly robust to data starvation. This robustness leads to a counterintuitive finding about sample efficiency. Imagine showing 1 billion tokens to a small model and a massive model. The massive one learns significantly more. Larger models minimize loss with fewer processed tokens. On the optimization curve, strictly in terms of data scene, the large model's error drops like a stone compared to the small one. It extracts more signal from every single word. But efficiency in data is not efficiency in dollars. We need to quantify the cost. Compute. C. The paper approximates this as C equals 6 times N times B times S, batch size times steps. Why the factor of 6? Because every parameter requires 2 floating point operations in the forward pass and roughly 4 in the backward pass to calculate gradients. 6 operations per parameter per token. That is the bill you pay. This brings us to the paper's critical insight on resource allocation. Suppose you have a fixed budget of $10 million. Traditional wisdom says, pick a model size you can train to convergence. Train it until it stops improving. The scaling laws prove this is wrong. Because giant models are so sample efficient, it is cheaper to train a very large model and stop it early than to train a smaller model to completion. The optimal move is to starve the model of convergence. You win by being big, not by being finished. The scaling laws paper moved the field from alchemy to engineering. It showed us that while we can't predict what a model will write, we can predict exactly how capable it will be based on the raw resources we feed it. We know the exponents, 0.076 for parameters, 0.095 for data. We know the overfitting ratio, and we know that in the era of large language models, the most efficient path is to build giants and train them just enough to unlock their potential.